Hello?
Yep. Can you?
Oh, hi.
Yeah.
I can hear you now.
All right, cool. I see a couple of other people in here that don't have their microphones enabled.
Yes, okay. Hi, Katie.
Hey, Elise.
Who's DJ? That's funny. There's Tim right there. Emma. Here, I'm going to try to, I'll little chat window over here. I don't exactly know what I'm doing, but I think, can you guys see this? So hang on. Emma, can you hear us? Can you guys see that?
Yeah, it like popped up on the bottom. Oh, there's Emma's face.
Oh,
Okay.
wait, it says that Emma's muted.
Yeah.
Am I unmuted now?
Oh, yes,
oh, yes,
you're
you're good.
Can you hear and see everything there?
Yeah, I think so.
Okay. Oh, DJ is Daryl. Cool. So, Daryl, can you see, hear us? So you guys can see that little chat window over there on the side?
We get like little notifications when you send something, and then we can choose to, yes, I guess if we click on it, we can open it.
Okay. So I'm going to talk to Daryl here for a minute just out loud. So Daryl, if you kind of hover your mouse over the screen and go down to the left over there, like by that little microphone, you can kind of click on the arrow next to it, and there's several options for audio and video that you should have. Oh, Daryl, can you hear now? Or can you talk?
Can you hear me?
Yeah, we can hear you, but we just can't see you. And also on the video part, there's a little, so again, if you hover over your screen and on the part, if you go over, oh, there he is. So Tim, same, oh, there he is. So can you hear there, Tim, then? Can everybody hear?
Yeah.
Mm-hmm.
Mm-hmm.
Okay, cool. So I don't, again, I posted all more videos than I think you could possibly want to go through, but I mean, I wanted to use this time, again, there's just too many variables to deal with as far as trying to make sure that Zoom works properly and make sure that everybody else gets it working. So that's why I wanted to just post a video. I think I'm going to continue to do that, but I'm going to use this time just to take questions. You can ask anything you want, and I'll just go through and we'll kind of adjust to the needs that people have. So do you guys have questions? Anything at all?
So, I could just be forgetting some stuff from Calc, but since the CDF is always continuous, does that mean that the PDF is also going to be continuous? Like in this case, the one we were doing, like you had the triangle where it met at the top. Is that always going to be the case that like the second piece is going to fill in the first? Does that make sense?
No, the
Okay.
the PDF does not have to be continuous, but
Okay.
remember, you're kind of slowly increasing X, right?
Right.
You're increasing X and you're accumulating area under the PDF, right?
Mm-hmm.
And if there's a break in the graph of the PDF, that doesn't really matter. So as a matter of fact, here, let me do some, it doesn't matter. It's still going to accumulate area at a continuous rate.
Okay.
So just because the PDF is discontinuous, that doesn't, the CDF will still be continuous in the continuous case.
Okay.
So here, let me do, actually, I'm just going to mess around with something here. So hang on a sec. Oh, wait. What am I doing? Let me go in here. Let me go to, I'm just messing around here. Let me see. So do you guys see a screen?
Oh, yeah.
Mm-hmm.
Okay, so let me do this. Can you see me like working in the screen?
Yeah.
So let me do this. I'm going to go into Desmos. So watch this. I'm just going to make something up here. Okay, so I'm going to say, I don't know, little f of x. I'm just going to make up some junk, all right? So little f of x equals, this is my PDF. So suppose I say that it's equal to, I don't know, like 0. Hey, in fact, oh wait, x less than 0. It's like 0. I'm gonna do a uniform distribution, okay? And I'm gonna do a uniform distribution on the interval from like 0 to 6, okay? So if I do a uniform distribution from 0 to 6, what would the height have to be between 0 and 6?
1/6.
A sixth, yes, because the total area under that curve has to be 1, yes?
Mm-hmm.
So let's say, okay, from 0 equal to or less than x, equal to or less than 6, colon, that needs to be a sixth. Okay, and we'll adjust the way this thing looks in just a minute. Okay, and then finally, if x is greater than 6, what does it have to be? What does the PDF have to be?
0.
Yeah, 0. Yeah. Okay. Okay, so there's that. Okay. Let me horse around with this a little bit. So let's see, -1, and let's go up to 7 on the x-axis. Okay, for the y-axis, I mean, that thing is obnoxious right now, you know what I'm saying? So let's go like -0.5. Let's go up to, I don't know, like, you know, let's go up to 1.2 or something, I don't know. Okay, so it at least looks not quite so obnoxious. Right, so you can see that, right? So if I were to integrate this thing, what would happen? If I were to integrate this thing, what would happen? Well, if I integrate up to anything before 0, what am I going to get? So that is, I'm integrating from -infinity up to wherever I am. If I integrate up to anything before 0, what am I going to get? I'm trying to come up with the cumulative distribution function right now, right? So if I integrate anywhere up to anything before 0, what will I get? I'm asking you guys.
Just 0.
Just 0, yeah. Okay. Now, what if I integrate up to some value that happens to be between 0 and 6? Okay. What if I integrate up to anything that happens to be between 0 and 6? So some x value between 0 and 6. What do you guys think?
6x.
Well, I'm going to be integrating the function 1/6 from 0 up to that x value, yes?
Oh, right.
The PDF
Oh.
density is the thing you integrate, yes?
Mm-hmm.
So you would be integrating the function 1/6 from 0 up to that x value, because everything else before 0 vanishes, yes? So what would the value end up being? 1/6. 1/6 what?
X.
Yeah, 1/6 x. Exactly right. Okay. And then, hey, what about x beyond 6? What is the total area going to be that I've accumulated from 6 onward? So again, I'm integrating this function that we have right here all the way up to something that's beyond 6. How much area will I have accumulated at that point? So I'm asking, so how much area will I have accumulated?
None.
Actually, all of it.
Oh, yeah.
1, right? I will have accumulated 1 at that point.
Right. Yeah.
Okay. So let's see. Does this? So do you see the? Look at that. So look at the CDF, right? I mean that thing is continuous even though the PDF itself is discontinuous. Does that make sense? Because of the way that we're sort of accumulating area. And incidentally, what do you know should be the relationship between the CDF and the PDF? I sort of made a big deal about this, but if I take the CDF and take the derivative, what should I get?
The PDF.
You get it. Yeah, so you see how that thing just kind of goes right over the top of that thing.
Okay.
I mean, there are rigorous ways that we could actually justify that, but yeah, I mean, we can at least see that that's exactly what's happening here. Does that make sense?
Yeah.
All right, how in the world do I stop sharing this? Okay, like that. So you weren't seeing my face at all during that time, right? So you were just seeing the Desmos graph or whatever?
We saw like your face and a couple other people's faces on the kind of the side, but the
Mhm.
main
Oh,
was Desmos.
okay. Okay, but you still saw the Desmos thing
Yeah.
Yeah.
screen. Cool. It's like you know, it's making me look good here, and I have no clue what I'm doing. All right, so other questions. What other questions are there?
So from the homework for chapter 4, for 84, I saw part of the explanation that you sent Emma about that, given our questions. So does that mean that we have to like choose which balls we're talking about for part B in particular?
That's a good question. So Matthew, are you on here? Are you on here, Matthew?
Yes.
Oh, didn't we talk about this problem?
84, correct?
What did we multiply that by 10? Part B?
No.
What was the answer we came up with?
The probability or the expected value?
The expected value.
Okay. We came out to the sum from 1 to 5 of 10 choose 1, p sub I, and then 1 minus p sub I to the 9th.
Right. So I think that's what we said, right? Isn't that what I said in my
Yeah.
Mm-hmm.
okay. So yeah, I think we do have to right. So pi, okay, pi times 1 minus pi raised to the 9th. That's basically just looking at box I and saying one ball is going in there and the other 9 aren't. Does that make sense?
Mm-hmm.
But we still have to decide which ball's the one that's going in there.
So we're treating them as distinguishable?
Yeah,
Okay.
yeah, you combinatorialists are on high alert, right? So,
Just wasn't sure.
yeah,
But
right.
that makes sense.
Yeah,
Because I think we
So,
had talked
yeah.
about that. We just weren't sure, yeah, if they were distinct or
Mhm.
not. So
okay. Yeah, because in combinatorics, we're always obsessed with that, right? Are they distinguishable or not?
Right.
Yes, yeah.
Yeah.
Okay,
O-
thank
Okay,
you.
so yeah, so Matthew, that is consistent with what we had talked about before then, right? Are you there, Matthew?
Yes.
Oh, okay, yeah, okay. All right, well, other questions. What other questions do you have?
I had a question on when we were discovering, I think this is one of the earlier videos, and we were looking at, I think it was the PDF from, it was the one with the triangle again. So like the waiting time for the two buses of 1/25y and 2/5 minus 1/25y. That problem.
Oh, where the buses were just totally, or you're talking about on the video?
Yeah.
Where the buses was a totally irrelevant part of the problem.
Right. I was just trying to give you a clue of which problem I was talking about.
Oh, okay, yeah. Right.
Yeah.
I think in the video though, I said something about that. Who cares about the buses, right?
Yeah. Mm-hmm.
Yeah.
Yes.
Okay, so what's your question?
So in one of the parts of the problem, we looked at the probability of going from 3 to y to 8, and then we took the integral of that, and then we also did it another way, just looking at the base and height of the triangle,
Yeah.
doing it that way. So but my question is, we're talking about continuous, how it's like continuous, and so it doesn't matter whether or not it's equal to the object or not, or whether it includes things.
The endpoints, yeah, right.
The endpoints.
So 3 and 8, like it doesn't matter whether I'm equal to 8 or
Right.
equal to 3. Yeah.
So my question is, would it be the same thing? So if we took if it was from 3, which is less than or equal to y, which is less than or equal to 8, is that going to be the same thing as the probability of 3 less than y less than 8?
Yes.
And any variation of that?
Yes.
Okay.
Yes.
Okay.
Did you guys understand? I mean, I know I'm making a big deal about this, but I like, this is so critical. So if it's because the probability of being equal to something is 0. There is no way that in moving x from left to right that I'm ever going to hit a number that makes the cumulative probability jump. Does that make sense? That's why the CDF has to be continuous, yes? Whenever you see a CDF jump, what does that tell you has happened with the probability of being equal to a value? What does that tell you? So like if I'm going along, you know, I'm at 4, 4.2, 4.3, blah, 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 and then suddenly 4.99999, and then at 5, boom, the thing jumps up like that in the cumulative distribution function. What does that tell you is going on at 5?
The probability is greater than 0 at 5.
The probability is positive, right? So could that ever happen in a continuous distribution? No. So that's why you will never see a jump in a cumulative distribution function in the continuous case. Yes?
Mm-hmm.
So you never jump. Does that make sense?
Mm-hmm.
So that's why being equal is just not a big deal in the continuous case, although it was a very big deal in the discrete case. Now, there's going to be some times where you have to be very careful, though, later on. In fact, Matthew and I were just talking about this morning in office hours, where when you do certain approximations, you will approximate certain discrete distributions with continuous distributions later on. And when you do that, you really have to think about, okay, how am I going to do this approximation? And there you really do have to think about shifting things by half a unit or something like that. And it gets a little bit testy at times. In fact, I don't know. Hey, Matthew, with your permission, I actually edited that video this morning.
Okay.
Would it be, I'll do it with your permission so that I'm in compliance with, I don't know, what is that called? FERPA? I edited that thing and that discussion that we had. If you're okay, I'll sort of upload that to Canvas, if you're okay with that. Is that all right?
Yeah, that works.
That's a problem that some of you might not do for a little while. It's at the end of chapter 5, but it has to do with approximating a discrete distribution by a continuous one, which is really kind of where we're going with a lot of this eventually. So yeah. So I'll post that video. All right, other questions? Anything else? Anything else? Oh, I thought Daryl had a question, but it just sounds like there's a dog barking there. So do the videos work all right? For the most part?
Mhm.
All right. And don't forget, you have your, I gave you a quiz, right?
Mhm.
And does it make sense how to upload that thing?
Mm-hmm.
I made it completely, user friendly in terms of the files that I could have forced you to do like a PDF, for instance, but I mean, that would allow me to do more stuff with commenting and whatnot. But if you just want to snap pictures and upload that to Canvas, that's perfectly fine. Okay. So now is your time. I mean, if you guys would rather me do this in a different way, I mean, let me know. I mean, if you would rather that I just lecture live and Zoom, I guess I could do that. But if the videos are working all right, you guys all right with that so far?
Yeah, fine with it.
Okay. Now there are times, I mean, one thing I've noticed is that I can't do it for very long for a couple of reasons. One, sometimes it's like I might make a mistake and then everything will get kind of screwed up. One thing that's unfortunate about this medium is I don't get feedback from you all, like, hey, hey, Hammett, you just made a minus sign error or something, right? So I'll make a mistake and then I'll keep going and then I'll realize, oh man, I made a mistake like 17 minutes ago. And now I have to kind of correct all of that stuff. So what I'm doing to prevent that is I'll just try to do small bits. And there are times, I will say, where I'll kind of get carried away and then I'll keep going and then I'll realize, man, something's totally not right now. And then I'll have to truncate the video and it'll feel like the video just ends abruptly. In fact, that happened, I think, on one of the videos I posted. Did it just like end or something? Did anybody notice that?
Mm-hmm.
Did you notice that, Elise?
Yeah, there was one of them, but it wasn't like a problem or anything. It just,
Okay.
yeah.
Well, I'll tell you what happened. I think and then I moved over into like the other room or something.
Mm-hmm.
Yeah.
I made a massive error at one point, and like, well, it wasn't that massive, but it was obvious that something was wrong, and I was trying to like figure out in my mind as I was talking, what's going on here? Why is something wrong? Then I realized, man, I just have to pause and figure out what's happening. And so I ended up having to truncate the video like 15 minutes earlier. So it's easier for me to have smaller, like little chunks like that, just so that it kind of prevents that sort of thing from happening. And also it doesn't take so long to upload to Canvas. So I'm just going to keep kind of doing that. Okay. So hopefully that works all right for everyone. Any other questions? Tim, Daryl, you guys have been quiet. No questions from you? All right. Who else is on here? So let's see. Emma. Yeah, Paul's not in here. All right. And again, you don't have to come in here, I guess. This is just for you to kind of ask questions, make sure everything's clear. I will take these and post them into Canvas just so you have a record of what was said and how it was said, and just extra information for you to keep track of how things are working. Okay. What else though? Anything else?
So I have a question about theoretical exercise number 1, but I don't want to.
In chapter 4?
Chapter 5.
Oh, okay. Chapter 5. All right. Okay. Oh, by the way, this one reminds me, I still need to, I said the theory of probability people, I was going to actually show you or prove to you that the Pareto distribution was actually a distribution for any given parameter theta or k, but I'll do that like at the beginning of the next lecture. Okay, I kind of skipped over that real quick. Okay, so what was your question on this, Matthew?
So I basically just wanted to check my answer, but I looked back over it before entering the meeting and I have no idea what I was doing.
Okay. Okay.
So
you have this density, right? So hang on, I'm gonna try something. This is totally an experiment, so just bear with me here. Man, I don't know if this is gonna work at all. Let me see. What do you see right now? Is it like a whiteboard or something?
Yeah.
Oh, okay. So f of x is equal to, okay, so f at x, oh man, are you serious? This is going to be horrible, is equal to, okay, ax squared e to the minus b x squared. Okay, and that is only for x equal to or greater than 0. Okay, and of course it's 0. Oh, wow. For x less than 0. Okay, so the claim is that this is a density, right? The claim is that this is a density, okay? And it actually gives you what B is. But I think all we have to do, so what's the only requirement for this density? What would have to be true about it?
the integral from -infinity to infinity is 1.
Right, but anything below 0, what's that going to integrate to?
0. So
Right, so it's really just the integral from 0 to infinity.
yeah.
Know what I'm saying? So really, I just need the integral, whoop, from 0 to infinity. Oh my word, okay. And you know, we can like factor out this a, right? That's a constant, and it's going to be x squared. Oh man, x squared e to the negative bx squared. How would you integrate that?
I used integration by parts.
Ah, yes. Yeah, integration by parts. Nice. Okay, so how's that going to work? What would you put u equal to? Remember, like integration by parts, I always do this thing where it's like I, L, A, T, E. Yeah, it sounds like a 3-year-old saying I'm late or something, right? ILAT, so it's like inverse, trig functions, logarithm, algebraic, trig, exponential, and as you read this left to right, that's what gets priority as being put equal to u. So in this case, I have an exponential function and I have a algebraic function. So what would u be equal to here?
X squared.
Yeah, so u is x squared, which means that du is equal to 2x dx. Okay, and dv, well, that's like, oops. Actually, I don't know if we should let u be x squared. I reject that. Why? Okay, should u be x squared? Because I don't know how to integrate e to the minus bx squared. Know what I mean?
Yeah.
So actually, let's just let u be x. Then what's du going to be?
Dx.
Dx, 1 dx. So then what would dv have to be?
X e to the negative bx squared.
Yeah. Why? What would possess me to do such a thing? Dx. Oh my goodness, this looks like a kindergartner writing this, but I don't know if a kindergartner will be writing this stuff though. Okay, so then what's v? So v is okay. So okay, well, why? Why did I want this extra factor of x sitting here?
So that you can do a u substitution and it will get rid of that.
Yeah. So that's exactly right. Yes. So this is like going to be negative 1 over 2b, negative 1 over 2b e to the negative bx squared. You know what I'm saying? Does that work? You take the derivative of that, doesn't that work? Yep. I think so. All right, so then this thing is going to be equal to, okay, a on the outside, huge parentheses. It's going to be u times v, okay, uv evaluated between 0 and infinity. Yeah? Minus the integral of v du, which is minus negative is like plus. So it's going to be plus plus the integral of v du. In the world, is this going to work out? Plus the integral of v du. So this plus the integral from 0 to infinity. So there's going to be a 1 over 2b right here. Okay, and then what? E to the minus. Oh man. Hey, isn't this, so first of all, u times v is just this times this, right? What happens
Yes.
if I plug in 0? What happens if I plug in 0 when I multiply those together? What do I get?
0.
0.
0. Yeah. And what happens if I plug in infinity? I know that sounds kind of bizarre, but what I mean by plugging in infinity, I mean letting x go to infinity. What is going to win? There's x and there's e to the minus bx squared. What's going to win? One of them is going to infinity, one's going to 0. What wins, the exponential or the polynomial?
Exponential.
Yeah. So and this thing right here is going to 0. Yeah. The exponential thing is going to 0. This is going to infinity, but this thing just destroys the polynomial. Yes. So what does this whole thing go to? That whole thing is just 0. And I don't know. I'm getting nervous here. So but hang on. So a over 2b. That whole thing goes to 0. It's a over 2b times this integral from 0 to infinity. E to the minus b x squared dx. And what should this be equal to, by the way? What do you know this has to be equal to?
1.
1. So I think, so the problem is this right here. Can you even do this antiderivative?
I found a way to.
Okay, how did you do it?
So I used, I think I used u equals x times the square root of 2b.
Okay. Are you serious? I don't because this thing right here doesn't actually have, I don't think that this has an antiderivative. The value of this integral is doable. It's going to be some kind of weird square root of pi or something like that, though.
Yeah, so you can, I think what I did was I rewrote it as a normal distribution
Yeah. Okay.
and then just, I apparently got it to equal 1/2, but yeah.
So this thing is equal to 1/2.
And some other stuff, but
Yeah. This integral is kind of a famous one. Like the integral of e to the minus constant times x squared is kind of a famous integral that has to do with the normal distribution. But you have to do some weird things to actually evaluate it. You actually have to use multivariable calculus to pull it off. But you're telling me that there is a substitution that you did that actually worked, Matthew? You put
yeah.
equal to what?
I set u equal to x times the square root of 2b.
Put u equal to x times the square root of 2b.
So that b times x squared would be equal to u squared over 2.
You put u equal to 2 times, or x times the square root of 2b. That's what you did. Yes?
Yes.
But then what's du?
Square root of 2b
Yeah.
times dx.
Okay. So then what would this integral turn into here?
E to the negative u squared over 2
Yeah.
all over the square root of 2b.
All over the square root of 2b, right? So this would become a over 2b times the square root of 2b, yeah?
Yes.
times what? The integral. Okay, well, if x is 0, u still is at 0, right? And what if x goes to infinity? Well, u is also going to go to infinity. Okay, so it's still 0 to infinity. And this is going to be e to the minus u squared over 2. And then you're right, du. You're right, that's just the density of the standard normal, right? Or it's almost like the density of the standard normal, yeah? So what is that? You can actually evaluate that integral. Now it turns out to actually evaluate this integral, you do need to use multivariable calculus, but this comes from the standard normal of random variable, which is something we'll talk about soon. So what is the value of this integral then, Matthew?
The square root of 2 pi all over 2.
The square root of 2 pi over 2.
Yes.
Half the square root of 2 pi. Yeah, that actually makes sense to me. So this is going to be a times the square root of 2 pi, right? All over 2 times 2 is 4. And then it's going to be b square root of 2b, right? And can't you cancel some junk here? Like what else cancels?
The square root of 2.
Yeah, square root of 2's cancel. It's going to be b, it's basically b to the 3 halves, yes? So you get like a, so a times the square root of pi, right? A times the square root of pi over, over what? Over 4b to the 3 halves or something? Is that right?
Yeah.
Okay. So what does that tell you? Now you know what a is, right? Because after all of this was just equal to 1 overall. Yeah? All of that was just equal to 1 in the end. So you know that a has to be 4 times whatever b is to the 3 halves, all divided by the square root of pi. Yeah?
Yeah.
Is that basically what you got, Matthew?
Yeah.
Okay. I mean, that's something that eventually these guys will have to work out. So I guess it's worth it to kind of see that and to refresh ourselves on the whole integration by parts thing. Okay. Is this how you did the integration by parts, Matthew, or did you do something else?
I think that's how I did it in my head, but I didn't write any of it out. So
Okay. But does that kind of answer your question?
yes.
Okay. Is that the right answer, by the way?
That's what I got when I first did it,
Okay.
but the book doesn't have the theoretical
Okay.
problem answers. So
I'm confident that that's correct, but yeah. Yeah. All right. What other questions are there? So that was a nice little refresher on integration by parts, taking limits, all that kind of good stuff. What else? Am I back on the screen now? Yeah. Anything else? Well, hey, thanks guys for showing up. Again, I'm not going to sort of force you to come in here, but I'm hoping that it will be beneficial every time for us to show up and kind of talk through some things, sort some of the details out that maybe are a little bit hazy still. I'm just going to continue to post short, like mini lecture videos. I'll put several in there for a given day or whatever. And You know, I'll keep you apprised as to what things are going to be turned in. I think what did I say about the test? What did I say about that?
I think you're next week sometime. You'll get it signed.
Yeah. Because I think like the 18th or something is when it's on the thing. I think I'd like to get a little bit of continuous distribution stuff in our rear view mirror before we do some of that. But we'll revisit that soon. I don't know. I'm not like super confident that we're gonna come back. I don't know. You know what I mean? I mean, I don't know what 2 weeks is gonna do. So I'm just kind of planning that this is going to be the new paradigm for the rest of the semester. Let me think about that. Maybe I'll send out a test on Friday and just give you, several days to work on it or something like that. But I have to rethink how I'm going to do that. Okay. But don't forget to turn in your quiz. I'm actually going to take this session and I'll put it into Canvas as well, just so that you have access to that if you want. Other than that, I think that's all I have to say. Anything else? Any other questions? All right. Well, I'm done.
Thank you, Dr. Hammett.
Yeah, thanks,
Yeah.
Dr. Hammond.
All right. See ya.